Hello everyone, and welcome to this video on potential energy and systems. So for potential energy versus external work, whenever we're analyzing systems of objects, a system has potential energy if any conservative forces are internal to the system, meaning the agent of that conservative force is included in the system. If the conservative force is external force in the system, then it's said to do external work, and we're going to reinforce this concept using a couple examples. So start with just a quick example using potential energy, gravitational potential energy. So consider a scenario where a 10 kilogram box is lifted 1 meter above the surface of the Earth and held at rest. We're going to analyze this example using two systems described below. So the first system is going to be the box Earth system, and the second is going to be just the box. It's important to note here that by changing the system from the box Earth system to the box system, we're not actually changing any of the physics that's going on. All we're doing is we're changing the names that we use for things like work or potential energy in how we analyze the problem. So when we're analyzing the box Earth system, we note that the Earth is the agent of the gravitational force. The Earth is what causes the gravitational force on the box. And we know that the gravitational force is conservative. So because the Earth is included in the system, we can say that the system has gravitational potential energy. So we can calculate the gravitational potential energy using mg delta y. And we get that there is 100 joules of gravitational potential energy in the box Earth system. Now, if we analyze just the box system, we know that there's still the same gravitational force acting on the box of mg, or in this case 100 newtons. But that gravitational force is caused by the Earth, which is outside of the system. It's not included in our system's definition. So we see here that the box is lifted up 1 meter and the force is pulling down. So we want to say that the gravitational force does negative work on the box. And remember that conservative forces doing negative work is potential energy. But if we do not include the agent of that conservative force, we can't really call it potential energy in the system. We can only call it external work done by the force of gravity. And so when we calculate this, we're going to get that the external force done by gravity is negative 100 joules. So it's the same magnitude as the potential energy stored when we calculated the box Earth system's gravitational potential energy. So take a look at another example where instead of having a box in the Earth, we'll have a block and a spring. So we have a 2.5 kilogram block. We're pushing it horizontally on a horizontally mounted spring. We're given the spring constant, and we're given how much the spring is compressed when we do this. The first system we'll analyze is the block spring system. So the spring, being the agent of the conservative spring force, is included in the system. So this system can have spring potential energy, meaning we can use the equation US equals 1/2 kx squared. Plugging in the correct values into this equation, we should get that the block spring system has a potential energy of, or a spring potential energy of 1.125 joules. Now, analyzing just the block system, we see that the spring is exerting a force equal to kx on the block. And because the spring is not included in the system, that force is external, and it should do work on the block as it's compressed. So it's compressed to the left, or the box moves to the left, and the spring force applies to the right. So we're getting negative work here. And again, if the spring were in the system, that would be potential energy. Now we can't simply just use the work is equal to force times distance, because spring force varies as a function of the box's position. So instead, it makes more sense to draw a quick sketch of a graph and use the concept that the area of this graph is the work done by the spring force. So we see here that the area is going to be the height of this triangle, or the spring force, times the base, which is delta x, times 1/2. And we do have a negative sign because it's being displaced in the opposite direction of the force. Now, if we substitute in the equation for the spring force, Fs equals kx, we should see that our equation for the work done by the spring ends up being negative 1/2 k times delta x squared. So calculating our value for the work done by the spring, we're going to get negative 1.125 joules. So as we look here, we see that the spring potential energy is the same magnitude as the work done by the spring in just the block system. So in the block spring system, we say that energy is stored as potential spring energy. In the block system, we say that the spring does work on the block, or external work on the block. The reality is the physics is the same both ways. It's just what we're calling the spring force and the spring potential energy, or if we're calling it work done or external work done. So once again, the physics doesn't change when we rename systems. What does change is if we consider the system to have potential energy, or if we consider that conservative force to be doing work on the system. So as a takeaway, defining the system as including or not including conservative forces doesn't change the actual real-world physics of the problem, but it does change how we, the problem solvers, analyze it. It also changes the nomenclature that we use when we're analyzing the problem. For instance, instead of calling it gravitational potential energy, we just call it work done by gravity. And that's going to be it on this video on potential energy and systems. Thanks for tuning in, and I'll see you next time.